ideally, given a random variable x, we know the distribution of x. So, x might be normally distributed or uniformly distributed, but there are applications where we may want we might be interested in the distribution of some function random variable. For example, x squared. Maybe for whatever reason we want to know, well, if x is normally distributed, what would the distribution of x squared be? Well, in short, it ends up being a gamma random variable, but we'll emphasize the idea that we can apply expectation to get the mean and variance of the new random variable, but the PDF itself, its structure, may be a little bit more difficult to come by without applying some sort of technique. So this is where change of variables comes into play. And from calculus, this might be something you would have called U substitution. It's a way to deal with a change in the variable name. And quite frankly, so in the notation that we'll use here, we've used f of x to denote the PDF of x. Sometimes we've even said if it's a discrete random variable, probability that capital X equals little x. And we're going to use capital F sub x. This is not a partial derivative in any way, shape, or form. This is probability distributions. Capital F sub x of little x will denote that to be the CDF, or the cumulative density function of x. Remember, cumulative density function, its input is the value of x, and its output gives you the area to the left of it. So for example, if we had the normal PDF, or the normal curve, and what we wanted was, well, we in here could compute areas, right? We could say, well, I want to know the area from here and to the left of that. Well, instead of using the PDF, if somehow we could come up with a function that accumulates all of that area, and may look something like this, where eventually it gets up to 1. Well, in that case, if this were, say, x equals 3, then here we could just plug in x equals 3, and it would tell us exactly what that total probability is. So the output would be the probability of x being less than or equal to 3 in our little mini example here. So that's what the CDF does. Now, back to the idea of knowing what the distribution of x is. So in this case, let's suppose that x is uniform between x equals 3 and x equals 8. So all that means is that between x equals 3 and x equals 8, we have a uniform distribution. So it means every value, every range, fixed range of values between x equals 3 and x equals 8 has a constant density, right? Equally likely. And so in that case, well, if the area under here, we're not explicitly given the PDF of x, but we know the area has to equal 1. And therefore, in order for this rectangle that has a width of 5 units, it has to have a height, it has to have an f of x, which is constant, right? Because it's going to be the same all the way across, such that 5 times f of x is equal to 1, right? So the area of that rectangle, and that means that f of x is equal to 1/5. So it's simple enough, probability density function. But let's say that what we want is we want the PDF of y equals x squared. Okay, so if we wanted that, then we could begin by writing the CDF of y. Okay, it just works out to be a little bit easier, as you'll soon see. So the CDF of y, the cumulative density function of y, would be, by definition, the probability that this new random variable y is less than or equal to little y. All right, so that's the definition of it. And, well, that further means capital Y is equal to x squared. So we can substitute in x squared for capital Y, and that would be, now in terms of the random variable that we started with, well, if I take the square root, and I'm not going to do plus or minus because I know that x is only defined within the window 3 to 8, so I'll just write positive square root of y, like that. Well, that has now set me up, and the reason we used the CDF was so that we could get a probability statement, and then we could formulate an integral based upon that. Well, by definition, that's going to be the integral of our PDF, which is 1/5. And it's going to be the area, right? So what we want this integral to go from is we want it to go from 0 to, or I'm sorry, from 3 to the square root of y. So basically, we want this in our PDF, right? Because that's where x is defined. It's defined on that interval. And we want it to go from 3, right? Everything less than or equal to square root of y, but not below x equals 3, because again, that's where our boundary is. So somewhere in here, I don't know where, somewhere in here we'll have x is equal to the square root of y. And what we want is we want the area in that region right there. Okay, so all we're doing here is we're just changing the name of the variable. And now I'm going to be careful here. I'm going to use dummy variable here, and I'm going to change the variable to t, right? Because I don't want to use x and y. I'm not integrating with respect to x or y. I'm integrating this function 1/5, but I want that value of t to go from 3 up to the square root of y. Okay, so it's all going to be in terms of y anyway. I don't want to use x though because that's going to get a little convoluted. It's not our random variable. Our random variable here is the square root of y. Okay, so that means we're going to have 1/5 t evaluated from t equals 3 to t equals the square root of y. And simple enough, okay, so we just plug in the square root of y, so we'll have 1/5 square root of y minus 3/5 when we plug in 3 for t and multiply it by 1/5. So that means, once all is said and done, our cumulative density function of y, okay, cumulative, this function accumulates areas, is 1/5 square root y minus 3/5. That is now in terms of, all in terms of y. Okay, now if we didn't want the CDF, we wanted the PDF. So how do we get the PDF? Well, the CDF is the integral, it accumulates all of the area, so the PDF is the derivative of the CDF. PDF is derivative of CDF. Okay, so I want to take the derivative with respect to y. So f of little y will equal the derivative with respect to y of the CDF, right? Because I don't want to accumulate area, I just want to know the density. And that's going to be the derivative of 1/5. I'm going to write this as y to the 1/2, make the derivative a little easier. And its derivative will be, this will be negative 1/10, or I'm sorry, positive 1/10. Take the derivative, use the power rule, 1/5 times 1/2 is 1/10, y to the negative 1/2, and then the derivative of negative 3/5 is 0. Now recall that our value of x was constrained between x equals 3 and x equals 8. But we're no longer dealing with x, we are now dealing with y. And because we know that y is the square of x, that means the boundaries on y are going to be different than the boundaries on x, right? X went from 3 to 8. But y is going to go from, write this out, if x goes from 3 to 8, then y, which is equal to x squared, well, it's got to go from 9 to 64, right? Because these are the squares of the value of x. So if we change the variable from x to y, we now have to think in terms of the boundaries for y. So this is the PDF of y, but it's defined for y between 9 and 64. And then I guess you could write it like this. You could say 0 else, meaning that outside of these boundaries, we would define the PDF to be 0. Is it important to do that? Well, sort of, right? Because this defines it in that interval, but what is it outside the interval? All right, so that's one way in which we could do this is, change the boundary of integration. But what did we really do here? Well, we could have approached this through pure substitution. By substitution. So let's consider again the probability statement. X is less than or equal to the square root of y. And that's the integral from x equals 3 to x equals square root of y of 1/5 dx. Okay, that's by the definition of our PDF, right? Integrate from x equals 3 to x equals square root of y. Now, let's do a substitution. Let t equal x squared. Okay, now that means that dt will equal 2x dx. And that means that we can replace dx with 1 over 2x dt. Now, since t equals x squared, that means x equals the square root of t. We don't need plus or minus in this case. And so now we can say that dx equals 1 over 2 square root t dt. All right, so basically we're using integration by substitution here. And that means that if we want to reframe this in terms of t, which is this new variable of x squared, then we also need to change our boundaries, right? X goes from 3 to the square root of y. And since t is equal to the square of x, that means t will go from 9 to t equals the square of x, which would in this case just be y. So our new integral will be the integral from t equals 9 to t equals y of not 1/5 dx anymore, but this will be 1/5 times 1 over 2 square root of t. And this is a real kind of roundabout way of doing it, but here lies more of the logic of calculus. And this is our PDF, right? So notice that there's the 1/10 y to the t to the negative 1/2. By the fundamental theorem of calculus, if we take the derivative with respect to y of capital F of y sub y of y, which is this thing here. Well, then by the fundamental theorem of calculus, that should simply be the argument right here, which we should call f of t, produces f of y. All right, and that just means that this will be 1 over 5 times 2, which is 10 square root square root y, because the substitution is made. And that is the same thing as 1/10 y to the negative 1/2 for y between 9 and 64. So same function there. And remember what this produces? When you take the derivative of the CDF, that gives you the PDF. We already wrote f of y. We have the same thing here and here, but just to emphasize on the left why we're taking the derivative, we want to get the PDF. Now, the change of variables in calculus, we call the method, the technique is integration by substitution. And the process involves transforming the CDF of y into an expression that is a CDF of x, which is what we did in this step right here, where we went from here to here. We got it in terms of an expression in terms of the random variable x. Differentiate the CDF to obtain the PDF of y. So those are the steps in solving for the PDF of this new random variable. Now, as just a comparison, I want to go ahead and I wanted to go ahead and paste this PDF so that you could see that while the PDF of x it started off as a uniform distribution, and now down here we have the PDF of y. As you can see, it's defined on the support from y equals 9 to y equals 64. Again, if we were to accumulate this area, you would get an area of 1. And that random variable, just by squaring a uniform random variable, you get this type of random variable, which doesn't expressly have a name, but it is the square root PDF, I guess, if you want to call it that. And so this just illustrates two ways of writing and producing the distribution of a function of a random variable.